Again, I want to consider the ionic compounds where cations and anions do exist. In Schottky defect, complete pair, one anion and one cation, leaves the crystal. Leaves the crystal lattice means absence of cation and anion pair in a crystal, ionic crystal. That is nothing but the Schottky effect. So, what is the effect of Schottky effect? Where can we apply that? Let us see in detail Schottky effect. Schottky defect, a stoichiometric point defect, is labeled after a scientist Walter H. Schottky. In 1930, he brought to the notice that cations and anions both can leave the place from the crystal, causing the vacant site at their position. For example, if I consider sodium chloride, then in crystal, one sodium ion and one chloride ion will displace from the crystal, will leave the place completely. So such defect is called as Schottky defect. Diagrammatically it is represented. By blue color, sodium ions, small ions are represented, and by red color, large ions, chloride ions are represented. From the crystal lattice, both ions, so a pair of ions, sodium and chloride, went out, causing vacancy at their original position. If you have to represent it in reaction way, then sodium and chloride ion, which were there at their original site, because of their removal, because of their absence, voids are created, gaps are created, vacancies are created. So vacancy of sodium plus vacancy of chlorine will be the result of Schottky defect. Surprisingly, defect is a need of a crystal for its stability. We consider equilibrium, thermodynamical equilibrium. What exactly that thermodynamical equilibrium is? To produce the defect, energy is absorbed. So absorption of energy is not a suitable way for the stability. But due to absorption of energy, some defects occurs, chaos increases, disorder increases, means entropy increases. The increase of entropy to such a level that stability is governed. So there remains a competition, there remains an equilibrium between the stable state, perfect state, and the defect state. At the beginning, you will find the total net free energy, gives free energy, decreases. Afterwards, it what increases. So at particular temperature, always there remains a minimum position for the free energy change, and that is the equilibrium position for that temperature. And that equilibrium position is the most stable position. If you read that equilibrium position, you will find number of defects certainly will be there. Means if you consider the crystal at room temperature, number of defects certainly will be there. As temperature increases, number of defects goes on increasing. Schottky defect is one of the defect. Relative to Frankel defect, more energy is necessary, more energy to be absorbed, then only Schottky defect is what possible. There are crystals which show the both defects, Frankel and the Schottky. So thermodynamic equilibrium and the importance for the occurrence of defect might be clear to you. Mathematically, we can represent the number of Schottky defects Ns is equal to capital N, means total number of the sites for cation or anion in the crystal, into e raised to minus delta H. S is represented, S for Schottky, the heat absorbed for the Schottky defect, divided by 2 kT. K is a Boltzmann constant and capital T is absolute temperature. With increase in temperature, Schottky defect increases. Let us know how the ion can migrate. For example, here I have shown a sodium ion vacant site. Similarly, other where in the crystal, chloride ion vacant site will be there. Now, vacant site is an unstable situation. Neighboring sodium ions wanted to change the site, wanted to change the position, and they wanted to go in that vacant site, creating vacant site at their own. So that this drama remains in continuation and the mobility of the ion is possible, or crystals show the conductance. And because of that, many properties are there, many applications are there. Now here sodium ion, if it has to migrate, then it has to jump and then has to go to the other vacant side, other corner. Translatory motion, in that plane it can't move because crowding is there more. Upside gaps are there. Where gaps are there, it will jump and then go out. Then to do all those things, it needs the energy of activation. Yes, that will be clear by the graph. See here. Start jump means original position of the sodium ion. Through the energy of activation, it has to move and then the landing will be there. The end of jump will be there. Means in vacant site it will go. Why it has a desire to go to the vacant site? Because vacant site is an unstable situation and other neighboring ion wanted to achieve that site. Because of that, what happens? In its own site, vacancy gets created. So that continuation of the mobility of the ion that we observe. But for that, some energy is necessary, that we say as the energy of activation. Schottky defect is a defect where both cation and anion in equal number leave the place. I said for sodium chloride. What about calcium fluoride or calcium chloride? How many cations and how many anions will go? One cation and two anions will go. Total neutrality will be maintained. Number of positive charges went out and number of negative charges went out will remain the same. Don't misunderstand that only one cation and only one anion moves out. Because of this movement of the ions or ions leave the complete lattice, the mass of the crystal lattice or crystal decreases, causing decrease in density. Volume there is a no change, but because of decrease in mass, density decreases. And because of the gaps in between, the strength of the material, strength of the crystal also decreases. This effect generally is observed in the ionic compounds where coordination number is high. Examples for this Schottky defect, they do bear the rock salt structure. And examples are sodium chloride, potassium chloride, cesium chloride, and silver bromide. The silver bromide shows Frankel defect also. Here is the importance of Schottky defect. We might have heard lithium battery for cell phone or other electronic equipment. That lithium battery can work more properly if it has more Schottky defect. In true sense, crystal works as a electrolyte and small lithium ions, that's the cations, do pass through the crystal, do migrate through the crystal, do transfer the charge, and these are the spill proof long life batteries for people to prefer such batteries. So lithium iodide purchasing is one of the example that I have shown to you. Such many other are there. Other kinds of defects also are used. But anyhow, defects are important for improvement in conductivity. That point I wanted to emphasize. As a homework, three simple questions. In order to occur the defect means among Frankel and Schottky, which defect will need more energy, whether Frankel or Schottky? Write answer in the comment box. Second question, can crystal work as an electrolyte? Is it possible? Yes or no? Third question, among these two defects, Schottky defect and Frankel defect, those are included in your syllabus for stoichiometric point defects. Which defect does not undergo change in density? Their resultant decrease or increase in density does not occur. What is the name of the defect? Schottky defect or Frankel defect? Write answers in the comment box. I am waiting for your answers. In detail discussion about the Frankel and the Schottky we did about the ionic compounds. They do occur in metals also, but I restricted our study for ionic compounds. Don't misunderstand that these effects. Reason for that, is suppose in a metal, one of the actual metal site, in spite of occupation, that metal goes in the interstitial site, then that's a Frankel defect. There's no change in the composition. So it's a stoichiometric defect. And in case of Schottky defect, if metal leaves the place of the crystal, means it doesn't remain there in the crystal, the gap will be created. What is the formula? Formula also doesn't change. Therefore, these defects are called stoichiometric point defects, and such any stoichiometric point defect can be considered in the category of Schottky or Frankel.